All right, so this is Spencer and Brady, lesson 12.
Hi.
Um, get number one. Brady will hit two and three, and then I'll end with four and five. So let me just get this screen share going. Brady, how's your Friday going?
It's amazing. I love doing genetics on Fridays.
Oh, yeah.
So fun.
Sorry, I forgot what I was doing. Okay. Number one. So just like, I don't know, the past few weeks, you just, which of the terms above? All right, so for A, we have which of the terms describes or is an example of a regulatory protein? And so we put the activator, cap, and repressor. So activator, cap, and repressor. B, which of the terms describes or is an example of a small effector molecule when you put inhibitor? C, which of the terms describes or is an example of a sequence found within the DNA? So we got our +1 sequence, the -10 operator, LAC-A and LAC-Z. D, we have which of the above is not involved in the LAC operon? And so we put inhibitor. E, which of the above is an example of a structural gene? So we put LAC-A and LAC-Z. Go ahead, Brady. Take it away.
All right. Number two is fill in the blanks. A, we have the lac operon is regulated by two inducers, blank and blank. We put, and I'm going to slaughter half these words, but if you guys want to leave a comment on how to pronounce them, that's your deal. But we got alactose and C amp or camp. I just say camp because it's easier. For
I
B,
like it.
we have the binding site for sigma factor and RNA polymerase is called LAC-P, while the cap site is the binding site for activator that regulates the LAC operon. C is the enzyme adenylase converts ATP into camp.
You're doing a good job.
Yes. D is the -35, -10, and +1 sequences are found within the LAC-P portion of the LAC operon. E, the LAC-I gene encodes the LAC repressor, while the LAC-Y gene encodes lactose polymerase. I got popcorn in my mouth. Leave me alone. F, attenuation can regulate gene expression in bacteria by causing transcription to terminate prematurely. And G, an E. coli strain that contains two copies of the LAC operon, is called a Mirazote strain. And you could see that in the video, the 11-minute video. I don't know what the title was. It was a good drawing, though. Number three is just coming from the bottom of the notes and using a little bit of innovation. It gives you your scenario up here. When it says for A, IPTG is present, glucose is absent, and XGAL is present. So if IPTG is not there, then the repressor bound to LAC0 is not working, from what I understand. No glucose levels mean that there's high camp levels, and the camp binds to the cap, and the cap binds to the cap site. And this beta galactosidase is produced, and XGAL won't cleave, so you will not have your color, if I am saying that correctly. For B, IPDG is present, glucose is absent, and XGAL is present. And so the repressor will I pretty much copied and pasted these. The repressor will release the LAC0, or the LAC0 will release the repressor. And the glucose means that there's high camp levels again, since it's absent. And the cap binds to the cap site. And this time, the XGAL is present again, so it won't cleave. For C, IPDG is present, glucose is absent, and XGAL is absent. So right off the bat, since XGAL is absent, you're going to know that your solution is not going to turn a color. But it will still, LAC0 will still give the repressor. No glucose means the high camp levels. And then your galactosase is produced, but the solution will not turn a color. IPDG is present, glucose is present, and X-gal is present. So when glucose is present, you're going to have a low camp concentration. It will not bind to the cap, and the cap will not bind to the cap site. And you won't have a color because the X-gal will not cleave. For E, we have IPTG is present, glucose is present, and X-gal is absent. So we put IPTG repressor is released by LAC0. Camp levels will be low since there's glucose present. The cap will not bind to the cap site, and galactosase is not produced, so X-gal will not cleave. So number 4.
All right, yeah, that's kind of just like the prep problems we did earlier in the week. All right.
Sure thing.
Let me go back to this screen share. All right, so number 4, it's asking us, is this our key that the negative sign or the minus sign is a defective gene and the plus is wild type gene. So it's giving us these different genotypes, and so it's asking if it's going to give us constitutive, inducible, or non-inducible expression of the LAC-Z gene. So for A, we have the genotype where everything's wild type, so we'll have an inducible expression. And then B, we have a non-inducible expression. And then C, we move to a constitutive, which just means that all the genes are on. D, with this genotype, we'll end up with inducible expression. And then E, once again, we have constitutive. So all the genes will be on. And then if we move down to number 5, this is referring to the experiment. And so basically, once again, we have our key where the minus is defective and the plus is a wild type gene. And so basically what we came up with, which hopefully it's right, is that for A, for the E. coli, we get 0 for both. So we're not going to have defective for the lactose. B, we're going to have 1 of each. So wild type and defective. C, we have 2 wild type, and we got 1 defective. And then D, we got 1 wild type and 0 defective. And then for E, we got zeros once again, just like A. So they're 0 defectives. So that's kind of how we did ours. Hopefully we did all right. Hope you guys enjoyed the video. We'll sign out now.
Peace.